All right, we are back at it with the Xanadu Quantum Codebook series, Introduction Part 8. Specifically today we are talking about the state preparation. So we have a nice list of gates over here, their associated matrices, and what they do on the 0 and 1 state. So first thing we can do is look at the problem, and the problem is to prepare the qubit in the following state. So how do we get it there? So we need to, they're equal probability, right? Because this exponential factor when multiplied by the conjugate will go away. So it seems like the first thing we can do is apply the Hadamard gate to the qubit. Once again, although it bugs me that it's not aliased as H, I did remember to type it this time. So now we have this state here without the phase factor on the 1. So how do we get that phase factor? Well, let's see. We can apply the T gate 5 times, presumably. It's probably an easier way to do it. If we remember that we can simply go over here. Well, let's just do the T gate 5 times. That seems like the most trivial solution, even if it's not the most efficient. You could obviously reduce this because remember, 2 T gates is an S gate. I'm trying to remember the exact decomposition of how many goes into all of them. So if we want, this should be correct. This is going to be a little awkward. Oh, I don't think I can try again. Yeah, I can't try again. But you could also just replace these two with S's. But that's just sort of the trivial understanding of how to get there. Now we want to write one that is not an equal superposition. All right, so how do we go about getting here? Looking at it trivially, we see a positive and a negative. So it looks like an Rx gate was being applied here from a 0 state. So now we just need to figure out, okay, what would give us cosine of theta over 2 would give us square root of 3 over 2, and cosine of theta over 2 equals. So maybe I'll just go to calculator online, very nice Wolfram alpha, and we'll do the inverse sine of 1/2. We can see that this is pi over 6. So now let's check cosine of pi over 6 square root of 3 over 2. So we can see that these all line up. So we want to do qml.rx, not pi over 6, but because remember this is cosine of theta over 2, so pi over 3, and this should be our state. And now we got a notification from Edge. All right, so we also have a template. Subroutines that can be used like any other gate. Templates have angle embeddings, basic embeddings, squeezing, IQP. I'm not familiar with IQP embeddings. Is non-differentiable. Let's see. See, this is an example, right? Where amplitude embedding is kind of cheating because although there are ways to encode it into the amplitude, it's difficult to do. But on a simulator, you can just set it up arbitrarily. So you can't differentiate it. Oh, this is... Oh, I know this paper. I didn't realize that that's what that came from. I believe in Qiskit, it has a name called ZZ feature map. But that's not important. Okay, Matonen state preparation. is also not something I'm familiar with. Let me check it. Oh, never mind. I am familiar with this. Don't know all the names though. So this is a way of preparing amplitude embedding using 2 to the n C0 gates and 2 to the n 1-qubit elementary rotations. And you can see here why amplitude embedding is something of a challenge, because although it's exponentially more efficient than sort of classical processing, it requires an exponential number of gates. So kind of evens out, I guess. All right, so we want to do qml. Really gonna make me type this out. I'm not gonna type that out. State vector wires. All right, so we have our state vector and we have our wires, 0. Oh. Error, function has no attribute construct. What am I doing wrong? Let's see. You need only pass the template and normalize in a set of wires. Oh, does this have to be a list? I don't know what that is. Oh. I should probably call this state. And then I should do wires equals 0. No. Create a node that uses this state preparation to prepare a qubit in the state V and return. Do I just need to put 0 here? Don't understand why this is saying. Let's see. Wires iterable. Okay, so it does need to be an iterable. I don't think an int is iterable. Okay. Oh, do I have to actually specify both of them? That would be very annoying. Wait, I do not Oh. I think the problem is function has no attribute construct. Okay, I don't know what the error is actually. Let's just look this up. I think it's because we're trying to pass the function. Okay, I do not know why this is going wrong. All right, let's look at their example again. So we have let's just take this, I guess. They know what's up. State vector must be of length 8 or less, got length 2. 4, yeah, so this seems about right. Okay, but what is going on here? Okay, I'll go in depth and read it now. Oh, is it because... Oh my god. I think I know why. It's because we don't have a... Okay, yeah, this time I'm just blind. This is my bad. It's because we don't have a device here. So this is just a function. That's... Okay. Sorry for the confusion, but I was confused there. I completely forgot you have to do this whole device thing. All right, but we got it. We did it. Next lesson. So far, we've learned about measurements. Now we learn about projective measurements. All right. So we can change bases and measure different bases, basically. There's also what does it stand for? POVM, projective operator, positive operator value measure. So we can introduce ways to increase the probability of basically measuring different things. So remember, if we have non-orthogonal states, we can't trivially tell them apart, because if we measure them, there's a chance we'll get one or the other. So we can do techniques to change that likelihood. All right, apply Hadamard and measure. So we want to do apply the wires, or the Hadamard on the wires. All right, that's pretty easy. All right, now we have different bases. All right. First, implement a quantum function that takes the state, that prepares the state, then determine how to prepare the basis states. So first we want to do this example here, 1/2, and that one. So if we go back, you can see that this is very similar to this approach, where we have this. Oh, well, I guess we don't even have to worry about doing that. We can just prepare the state as before. I was going to say we could do it with these matrices, but we can also just use our little cheating technique to prepare the state in this. All right, here we go. Now we have that sends both 0. Okay, so now we want to map them to the y basis. So we can do that by mapping it to the x basis and then rotating around the z-axis, I believe. So we can do what's the exact rotation? RZ pi over 2, I think. Let's see if this is right. Okay, so we put it into Hadamard, and then we need to map maybe it should be negative pi over 2. No. Okay, I'm just trying to visualize the block sphere right now. So we've put it into the z basis. Now to convert it to the y basis, we need to map halfway around the z-axis. Let me just check. If we want to, we can just go back actually and look at. I guess we can just apply a y gate here. Because if we remember, that just adds an I and a negative I, so. Oh, right. Poly y. No, that's not right. Oh, right. We want to do, we want something that just maps 1 to I. So we don't want the Y gate, we want the S gate. My bad. Which is actually the same as a rotation around Z in some sense. So now we want to produce the basis states. All right, prepare the state. So we want to call our function prepare psi, perform the Y basis rotation, return the measurement outcome probabilities. qml dot prob wires equals 0. All right. Okay, well, I know that these are both right, so that's good. And I can't change them either, even if they were wrong. What's the matter? Oh, right. We want to do the adjoint here. Oh, oopsies. No, that's not what we want to do. Let's see. Okay, now that we have the basis states, we can perform measurement in that basis. To do so, we must apply the adjoint operation of these operations to rotate back from that basis to the computational one. Using your quantum function from the previous exercise, perform the basis rotation. What exactly are we doing? Okay, so we have this state and we want to measure in the plus or minus basis. So then we can so we prepared a state. This seems right because the measurement is 0.25, which is 1/2 squared, and then 0.75, which is 3 square root of 3 over 2 squared, because that's then 3/4. So I'm not sure what's wrong here, but it doesn't like that answer. What happens if I undo this? Yeah, so that's not right. Does it want me to adjoint both of them? Let's see. Oh, oopsies. Yeah, I didn't think it wanted me to do that. Okay, now why is this not correct? It's giving us the proper outputs. What's going on here? What's the output supposed to be? No, is it because we want to measure? This basis? So maybe I'm measuring in a computational basis instead. What is going on here? Is apply the adjoint of the operations to rotate back. Do not know what is going on here. Maybe I don't understand the problem. So we have this state function. We want to make a measurement in the y basis. Okay, well, let's go back over here. I need to do some math. All right. So we have the state 1/2 0 plus 3/2 I1. All right, what is this in the y basis? So we have 1/0 plus I/√2 1 times some value times x plus this 2 yeah, I don't know why I cross out plus √2 0 plus I over square root of 2. It should actually be minus 1. All right, so then in this state we have I just do not understand. Let's suppose we had 50-50, right? Or 25. So we had 1/2 over here, and 75 is 3/4 over here. But we have to square root them. We would get 1/2√2 plus 3/2√2 0 minus I√3 over √2 2. Okay, let me think about this for a second. I feel like I'm missing just something trivial here. Because we want to measure in the y basis, which means we want to convert from the y basis back to the z basis by doing the adjoint. Is that not exactly what we want? I'm gonna check. Don't know if there are answers online, but if there are, let's see. Let's see if anyone else has had this problem. Let's filter by codebook. Exercise 1. Okay, that doesn't matter. What are we looking at? I9. Let's go over here. No, 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 no. No, no one has had any questions with that. Let's just check I9. All right, that's our problem. But what is the solution? Maybe there's at the beginning something I missed. Okay. I do not know what I'm missing right here. Okay, let me think. So that's mapping to the right basis. Let me check y basis. Yeah, that's the y basis. Well, it doesn't really tell me how to get to the basis, but that's fine. Okay, I didn't think I was going to solve it. I just saw this link over here. Let's check this. Okay, I don't know where that result even was. Why can I apply? Okay, because HS dagger converts it to the... All right, let's try again. Maybe I mistyped something. We have prepare. We want the adjoint of the y. Okay. Okay. I get why it should be working. I don't get why it isn't working. Okay, this is very frustrating. We've prepared the state. We want to make a measurement in that basis. I do not understand what is going wrong right now. Prepare to state, rotation back to computational basis state. Oh, this is very... there's something that I'm just missing here, and it's very frustrating. I'm sure it's just because I'm not reading something. Okay, well, I don't think I'm going to get it by just sitting here. So here's what I'm going to do. I think I will... I think I'll just do the math out and see what the answer should be and why I'm not lining up. So we want to do inner product. Let's see, can I do that? Wolfram alpha. So we want to do the inner product between this state, which is 1/2, and this. Actually, yeah, let me just check something. This should be the transpose of this. So we have 1/2 times 3 plus, yeah, so we have to transpose it ourselves. That's all I was checking. Negative i's times square root of 3 over 2 between this and 1 over square root of 2 I over square root of 2. All right. All right. So that should be about 93% one way. Let me change this to a negative now to just simply get this version. And this should be... Okay, so that adds up, should be 93 and 0. And we are not getting 93 and 0. Okay, so that explains the problem. let me check something. Maybe there's an error. So we have our Hadamard gate here. And we have our state here. So that's our new state. So now let's go and do our new state times the S gate. Diagnose exactly what's going on here. S gate is 1, 0, 0, e to the I pi over 2. Let's say that's right. I should really just look this up. Oh my god. Okay, there we go. Oh, it's just I. Which I think is the same thing, but that's not important. Actually, I think we were supposed to apply this. The adjoint of this would be applying this first. So I just realized it should actually be like this. And then we should do this. And then we should, let's see, what's the problem here? Maybe we can circumvent this somehow. Let's see if we can do this. Okay. So I don't know what the problem was, but the problem, infuriatingly, was actually nothing that I did wrong. It was the adjoint of this operation, because the adjoint of the Hadamard is just the Hadamards. So if I did, I mean, I can't edit this, but if I did it, it ought to be qml.adjoint of Hadamard. But I don't think that the adjunct of a function actually works correctly. Let me go back here, because I think what's happening is it adjointed the Hadamard gate and then the S gate and applied them in that order, when the adjoint of these two would be the S and then the Hadamard, I think is what's going on. Okay, I feel like I feel like it's a bold claim to say the TensorFlow of quantum computing when there literally is a TensorFlow quantum. I feel like it's a bold it's a bold claim to make, but I guess they can do that. I'm just gonna look at the adjoint because I don't think this is. Yeah, I see what's going on. I think it's. No, it should be working right. I don't know why. I don't know what was going on with the adjoint over here then. But I guess that's long enough for today because that took so long. Something weird is going on with the adjoint that because I just manually did the adjoint and it worked. So I don't know what was going on with that. But I guess we can call it there.